Welcome. My name is Mima Stanojkovski and I am part of the Nonlinear Algebra group. I came to this institute in 2019 and I just recently joined a position between the University of Aachen and the MPI Leipzig within the SFB collaborative program, Symbolic Tools in Mathematics and Their Applications. Today I will be talking about groups from determinantal curves and joint work with Christopher Voll, with a particular emphasis on p-groups. So why groups and the sciences? Well, groups arise naturally as symmetries of objects. So they are naturally to be found everywhere in mathematics and in the sciences. And symmetries of objects help us understand objects better or tell the object in question apart from others. So we can think of them as an invariant of the object we're looking at. And in the fortunate case in which we end up working with finite groups, then we have several ways of understanding their structure. Externally, we can look at their composition factors, which are finite simple groups. And internally, thanks to zero theory, we know that we can find p-groups within. Let me just remind you that a finite p-group is a group that has order a power of a prime p. And another reason for looking at p-groups is that most finite groups are actually p-groups. This is an asymptotic statement, but just as an example, if we look at groups of order at most 2000 and we count the isomorphism classes of these groups, then 99% of these groups are two groups. So p-groups for p equal to 2. It seems, however, that classifying p-groups is a very difficult task. So to quote Philip Holl from 1940, to put it crudely, there is no apparent limit to the complication of a prime power group. So why is that? Why are they so difficult to classify? Well, let me tell you this with a quote again by Magnus from 1937. The main difficulty does not lie in the construction of groups of a given type, but rather in the specification of a complete set of representatives of the constructed groups. This is my own translation from his German wording, but this should be more or less the content. And let me tell you something about why these groups are so difficult to tell apart. So, in general, if we look at the group isomorphism problem computationally, we do not know whether we can tell two finite groups apart in polynomial time in their order. We do know, however, this for certain families of groups. Namely, for example, we know this for finite simple groups, and this is also a result of the classification. The most difficult class of groups to tackle seems to be the class of groups of p-groups. And the case that people are really trying to study nowadays is that of finite p-groups of class 2 and exponent p. So this class of groups, some representatives of them we will see also today. So you see, telling groups apart by their isomorphism type is still up to date a difficult task. It's also as difficult to count these groups. So if we want to count p groups, we have formulas for doing this up to order p to the 7. Beyond that, we don't know how many we have. And Higman in 1960s formulated his famous poor conjecture that deals with certain properties of these counting functions. So I want to show it to you. If we fix an order p to the n for the groups we want to look at, where p is allowed to vary but n is not, Higman conjectured that this function describing the number of groups of this order is polynomial on residue classes. We know already that this function will not be polynomial in p, but the conjecture is it will be polynomial on a finite number of cases, namely the residue classes of p modulo some integer n, depending on the given order. The existing formulas support this conjecture. So up to order p to the 7, we know that these classes are given by polynomials on residue classes. How has this been proven for other classes is that, yeah, indeed, they don't look at a whole order, so all the isomorphism types of a given order, but rather some subfamilies, and then they add up the contributions. This conjecture has also been questioned recently by different authors. The example that I want to show you today is an example of Dussato and von Lee. And what they did, they started with a group and they built a family inductively out of it, and such that that family did not have counting function that was polynomial on residue classes. So I don't really want to tell you how this family is built, but let me tell you what the object was they started from. And that is the group GB that appears on my slides. And it's given by a presentation. So all the commutator relations that you don't see are supposed to be trivial. This is a P group, GP, for P odd, I should say. And it has a global component to it, namely the definition of the commutators. As you see, for every P, those are the same. How do we make it a P group? Well, we impose that the generators all have order P. So in some sense, if we look at it below, we can encode the commutators in a matrix, 6 by 6. So the actual generators that we need here are 6. So y1, y2, y3 are just derived from the others. And the matrix B tilde encodes the commutators. And from this matrix B tilde, we can build GP in the following way. We first build a global object, a unipotent group scheme, coming from B tilde, and taking the FP points of it, we get the group GP. In other words, we can also write down the presentation and we can allow the prime to vary because we know exactly where this will vary. Let me also remark that this matrix is antisymmetric because it represents an antisymmetric form. So we can as well just record, in this specific example, the matrix B tilde by its upper right corner. And then we get exactly the group we started from. And one thing I want to tell you, the reason why this example is very interesting is that the matrix B, if we take the determinant of it and we set it equal to 0, defines an elliptic curve, which is the elliptic curve you see on my slides in pink. Let me show you another example we constructed, getting inspired from their first construction. And you see, in nature, it is very similar. The presentation is slightly different, but again, it comes from a smaller matrix, 3 by 3. This is again a group of order P to the 9. And it comes from a global construction. And once again, the determinant of this matrix set equal to 0 defines an elliptic curve, which is the blue curve. These curves are isomorphic as elliptic curves over C. However, the two groups I presented once we fix P odd P will not be isomorphic. And this is a result of our work. So we know how to deal with groups that come in this shape. But in a moment, I'll tell you more about this. General idea of the work is that you can start from a variety or a parametrized family of varieties. For example, here we have curves. They can be smooth or not. I thank Daniele Agostini for this picture. And this variety or family of varieties, we encode somehow. We want to express them as determinants of a matrix of linear forms that we set equal to 0. From there, we define a global object and subsequently local objects by ranging over the primes, a bit as in the example we looked at. So let me get slightly more technical, but stay with the same diagram. Today, what we do is we start from an elliptic curve. we find a determinantal representation of it. Actually, we will be looking at symmetric representations. From there, from such a representation, we will define a globally defined group over Z, and we will project over the primes to get finite objects ranging over the primes. The questions we're interested in are, informally, how much of this curve, of the starting curve, do we see within the groups? And also, as we range over the primes, how does the number of symmetries of these groups vary? Okay, so before I tell you what our results are, let me remind you of the fact that an elliptic curve is a smooth projective curve that comes with the structure of an abelian variety. And so it makes sense to talk about its n torsion over a field K. So these are just the K rational points P, such that if we add them up n times to one to the other using the operation on the curve, then we get the zero of the curve. So here is a sneak peek to our main result. I simplified it here a little so we can look at it over the primes over Fp, actually. And it says that if our curve has 4 two-torsion points defined over Fp, then we can define 3 groups, G1, G2, and G3. There are P groups of order P to the 9, exponent P, and class 2. So very much resembling the curves we saw in the examples. And also, for these groups, we know we can describe the symmetries of the groups in terms of the geometry of the curve. And indeed, we can write the number of automorphisms of our P group as P to the 18 times GL2 Fp, the size of it. So these are standard factors times a factor that comes from the symmetries of the curve as a projective curve. Let me remark that for curves of a particular shape, so given, for example, by the equation y squared equal x cubed plus delta x, we know exactly what the subgroup of the symmetries of the group of the curve is. And also, we can tell any two groups that come from this construction, also from different deltas, we can tell whether they are isomorphic or not. And as I will tell you later, this has an implication in the understanding of the observed non-Park phenomena coming from the examples we've seen before. So let's get to it. Let me tell you how you build a group over Z from a determinantal representation. Here are the ingredients. We start with the matrix B of linear forms, a D by D matrix, a square matrix, with coefficients linear forms over Z. So B is going to be written as B1y1 plus B2y2, etc., up to BDYD, where BK is a matrix with coefficients in Z, and Y1 and YD are indeterminants. U, W, and T are vector spaces of dimension D over a chosen field K, and Phi is a bilinear map coming from the matrix of linear forms B via the equation that I wrote on the slides. So we send a pair UW to UBW transpose, and here I'm slightly abusing notation because I'm identifying the variables y1, yd with the chosen basis of the arrival space, T. And remember, our goal is to be able to describe an elliptic curve with this matrix of linear forms. So there is an example below for a two-dimensional case where B is simply a diagonal matrix with y1 and y2 on the diagonal. And there you see how you get the image of UW under phi, identifying y1 with the first standard basis vector E1 and y2 with the second standard basis vector E2. So how do we use this to produce a group? Well, not only we produce a group, we also produce an associated algebra, Lie algebra, that we will use later in our proofs. How does this go? Well, we take the direct sum of our three vector spaces and we twist the operation, so the usual operation coming from the vector space structure using the map phi. This is for getting a group. And for getting a Cayley algebra, we just have to define the brackets. And this we do also using the map phi. This is in particular a graded algebra because all the brackets live in T, so in the last vector space, in the sum. A bunch of examples. The group and the algebra, there will be a billion if and only if the starting matrix was the zero matrix. We get the Heisenberg group and the associated algebra whenever we start from a 1 by 1 matrix and with entry just one of the variables. If K is a finite field of P elements for P odd, then the order of G is going to be P to the 3D and the exponent of G is going to be P. So here I told you how to construct groups from matrices of linear forms. Let's see how we construct matrices of linear forms from elliptic curves. And here is a recipe for doing that so that the representations will be symmetric. And this is a recipe, so this comes from a theorem of Hesse from 1844 that tells us that there's three ways. We can get three symmetric determinantal representations of a given elliptic curve by solving this Hessian equation here in the last line of the theorem. And let me tell you that Hess here denotes the determinant of the matrix of the second derivatives. These representations will be inequivalent with the standard equivalence relation put on determinantal representation. But what interests us the most is that, well, now we have matrices 3 by 3 that encode our starting elliptic curve. Let me mention that these three inequivalent representations correspond to the expected three non-trivial two torsion points on the curve. When I say expected, I mean maximal number. So over the algebraic closure, we know that we always have three non-trivial two torsion points. And if the field is not algebraically closed, we don't know if we have three, we might have less, and the same number will apply to the number of determinantal representations that we get. In any case, this gives us the matrices that allow us to construct the groups and the algebras. So let's go back to our diagram. Now we know how to encode a curve into a matrix of linear forms, and we also know how to build groups and algebras from a matrix of linear forms. So how do we come back to localizing this global object when we range over the primes? Well, here is a slightly expanded version of the first theorem we saw. So either then we don't look at only prime fields anymore, so for a P, but rather any finite field is allowed of odd characteristic. And again, we ask for 4 two torsion points of the curve. Then we can construct three groups, G1, G2, and G3. There will be P groups of order the size of f to the 9, exponent P class 2. And we know exactly how to describe the order of the automorphism group of these groups in terms of the geometry of the curve. Here also I wrote what this number of symmetries coming from the curve looks like when we start from a curve in the shape y squared equal x to the cube minus delta x. And that indeed comes from two factors. One factor is given by the three torsion points of E over F, and the other factor comes from the fourth roots of unity we can see in the field. So if I is 1, that's really the number of three torsion points times the number of primitive fourth roots of unity in the field. If I is equal to 2 or 3, then we have a constant factor of 2 replacing that last factor. Great. So this in some sense localizes and tells us that if the number of symmetries, when we count this over the primes, is non-porc, well, The responsible factor for this are the number of three torsion points. A couple of words about the proof of this result. We use linear algebra techniques to start with via the Bayer correspondence, but then we have to be able to move from the field Fp to the extension F of it. And this we do using the fact that we use elliptic curves so that the objects encoded in our groups are elliptic curves and the result of Wilson. Once we've done that, we can really separate the size of the automorphism group of the F-Lie algebra into standard factors times something that really comes from the curve. And this we do by identifying a subgroup of the automorphism group of the algebra that maps into the symmetries of the curve as a projective object. The kernel of this map is easy to describe. The image is a little bit more tricky. So the blue factor really just comes from the fact that the algebra is graded. The green factor, so the GL2, the copy of GL2, comes from the fact that the matrix of linear forms is symmetric, and the rest comes from the fact that we are dealing with elliptic curves here. So some closing remarks are that thanks to our work, not only we are able to tell that the Dusserteuil-von Lie counting function is not quasi-polynomial, so non-pork, but we can say this for counting functions associated to many, many elliptic curves. And let me remark that this counting function, it's not pork, but it is polynomial for Frobenius sets. Other directions one could go into are now, well, sorting out this for not necessarily symmetric representations of elliptic curves, in general finding formulas for all elliptic curves, or moving to other interesting varieties. So let me close here. I thank you for your attention, and I invite you to check out our paper that is available on the archive and that has been accepted for publication by Mathematische Annalen. Thank you.